So, hi everyone, and thank you for joining our call. Without further ado, Maxim, dive in.
Hi everybody. Today I would like to tell about RGB release with the name version 0.10, which happens this month. And this release started with the release of consensus layer last month. And there was a presentation explaining how it has changed, evolved, and what's new. And today I would like to move into RGB application layer, specifically how RGB functionality can be accessed by applications and then by users. And with this release, we are releasing different components, which I will be showcasing today and explaining what these components do. And this is the process. So not all of these components are released, and the amount of information is quite large. So I splitted this presentation into presentations today and the next Thursday. And hopefully by the next Thursday, the release process will be also completed, and all these components will be out there. What I will be presenting today is already working today. So these things are released, and these things will be related mainly to the creation of new contracts and issuing assets and working with the asset states. And the next week, I will focus on wallet-specific tasks and sending assets between peers, sending contracts between peers. But let me start with what this new release is about and why it's quite important comparing to all other releases that we had in the past, maybe except the initial release of the RGB about a year ago, and comparing to the releases in the future. This is a milestone release because it adds and refactors a lot of RGB functionality. First of all, it has changed a lot in RGB consensus, which we described in a lot of details last month, but it also changes a lot for the applications which are using RGB. And by doing this release, our primary goal was to unlock the full potential which was already present in RGB platform, but wasn't accessible or wasn't fully completed or wasn't simple enough to be used by the developers and wallets and users. So by this potential, we tried to make RGB a real smart contract platform capable of everything that can be done on other smart contract platforms, but without the trade-offs that they have, like censorship, pronability, and so on. Confidentiality problems. RGB doesn't have that problems, but it was much harder to do more common things like global state or complex data types or programmability with the new client-side validation paradigm that RGB had. And finally, with version 0.10, we have completed that road, and I don't see actually anything that can be done in the other blockchain smart contract systems which can't be replicated in RGB with the client-side validation paradigm. So, and this actually the main feature of this release. And things which I mean by the potential of RGB as a smart contract platform includes stuff like adding a global state to the smart contracts, such that all participants of the smart contract can see that state and can act and validate RGB data basing on that global state. Also, it involves complex data types. So for now, state can be arbitrary data, which can be parsed and analyzed from inside the virtual machine. So you can structure arrays, lists, maps, you can create a hierarchical data types, trees, any complex data type that is possible to be implemented in Rust are now present in RGB. And even more, I will be showing that you can write data types in Rust and compile them into RGB smart contracts and use inside the RGB smart contracts. So that is pretty much advanced. And the level of how it is advanced is the fact that I was able to compile the whole RGB consensus library and put it into RGB contract itself. So basically it shows the amount of potential that this new update brings. Also, it adds a lot of programmability features based on Alluvium. Previously, RGB started without its own virtual machine. It was using predefined validation procedures specific to a very concrete types of contracts, like fungible assets, comparing that the sum of the outputs equals to the sum of inputs. And you can't do anything arbitrary with that. So we introduced later, about 2 years ago, we started introducing a new virtual machine designed specifically for client-side validation, which is pretty much different from the requirements that VASM had or other virtual machines had. So that's why we had to do something dedicated for the RGB. And today we finalized this thing, and now all validation of all smart contracts has moved to Alluvium. There is no more embedded procedures, these predefined procedures, custom procedures, which are kind of, they don't look good to have something predefined and hard-coded in the RGB consensus level layer. So they are all removed, and now all validation is done with the virtual machine, Alluvium. And this Alluvium is also able to introspect into contract state, into the RGB contract itself, and take this state into account during the validation procedure. So that adds the full programmability. In the future, like several presentations ago, I was explaining how RGB can be upgraded, that there is no such thing as forks, soft forks or hard forks, and there are different things called, which I propose to call fast forwards and pushbacks. And fast forwards is the way how you can bring a new functionality to RGB, not affecting the existing users and not affecting the ownership of existing assets. So the fast forwards will be the main path for upgrading RGB. And the future fast forwards will bring more programmability, extending the amount of Alluvium opcodes with the ability to introspect the state of the Bitcoin blockchain and the state of the Lightning Network channels. And finally, we have a new system of contract interfaces. I will spend a lot of time explaining today what contract interfaces are and why they are important, but briefly, they unlock ability for independent developers to do complex business logic in RGB smart contracts without the need for wallets to be upgraded or for any software to be upgraded. So it adds a flexibility of introduction of new functionality on the contract level into RGB without any code and and software updates. So that was the primary goal, make RGB a smart contract platform. And I think with the version 0.10, we finally at that goal. The next thing that we also focused during this release is the simplification of how RGB can be used by developers and users. And I will start with this part, and in the next few slides, I will be showing how much less components do we have in mobiles and desktop environments and how the integration has much simplified. This also resulted that we were able to add VASM support such that RGB with the whole smart contracts, its virtual machine, the strict type system can run inside the web browser. And all this validation can happen in the web browser without access to the file system. And finally, a side effect, a very good side effect of the work that we has done was the increase of robustness and determinism, because the introduction of this new type system, we call strict type system, functional type system, it helps us to probably detect any changes in the consensus layer such that, and make sure that the new versions of the software doesn't break any APIs or functionality or data storage formats. So that's why RGB version 0.10 is huge. And today I would like to give an overview of the details of all these features explain the anatomy of RGB smart contracts, which actually had changed with this release because of the introduction of these interfaces and new type system. Explain how to work with the interface, show how to use them, and demonstrate how to write RGB contract, issue an asset from both wallet developer perspective and end user perspective. The main things which came with a version 0.10 release, they came at 2 layers. The first one is the consensus layer, and it was presented last month, and it's already released. And the second is application layer, which I present today, and it will be also presented next week. And I already covered the tasks related to the consensus level when I was talking about this slide. So these all points are explained by me. On the application level, well, also these points are covered, though the only 2 things which I didn't mention is that we now have much better mobile support because we were able to get rid of zero message queue, which required C-level libraries and networking and was quite heavy-duty stuff on the mobile. We are able now to run RGB without own runtime, so the mobile wallets can use a custom runtime to manage the multi-thread in the way they like to. And it also unlocks the ability to do the backups of the data, because before it was much more challenging since the mobile wallet always had an RGB node running and accessing those data. And there is also a simplification of the desktop because now it's not required to run RGB node on desktop. You can work with a RGB without setting up a node. By node, I mean some program that constantly resides in the memory. You can actually do that much simpler. So I will start with these changes to mobile and desktop. Before, in mobile, the stack of RGB looked like this. So from the user interface to the actual RGB libs, there was a lot of layers in between with the networking and the node that had multiple threads and had its own runtime. With RGB 0.10, this changes into this thing. So user interface directly talks to the RGB code without any networking layer, and it uses JSON as an intermediary format, which allows to get rid of a complex API wrappers, which had to be written for the language-specific in the language-specific way, like for Swift, in Swift for iOS and in Kotlin for Android. Now that's all has gone, and basically there are RGB libs, which I will be presenting today. There would be a tiny layer of bindings because there would be just few API calls, which will all work with the JSON data. And the reason why it's also possible is because the strict type system, it has full convertibility between its own binary serialization format and JSON, YAML, or TOML formats, such that it can always serialize and deserialize from these structures. And it also can verify that the data provided in JSON exactly match the specification and the schema of the data which are expected. So it also helps to avoid many errors which can happen when you work with the JSON. On desktop, the environment which we had before today for RGB node was even much more complex. Actually, it was the same on mobile, I just didn't fit all the components in here. But basically, additional to the RGB node, there were also always another daemon which managed a database and storage of the data, also accessed through the zero message queue. And the user interface has to call RGB RPC library, which was talking to the local node, which was talking to the stored daemon. So it was, this is good for server-side environment, and we maintain this architecture if somebody wants to run a server with the scalability features, starting from RGB node on home box up to the exchange, which needs something in the cloud. But for desktop, that is not needed. And now this is the way the RGB will be working. Like everything that is excessive has gone, and this much simplifies the life of the developers. So this is the new library stack from the app developer perspective. And underneath, we have the RGB Core library, which is responsible for all consensus layer tasks, and also which does the validation of the consensus data. And this level that you do not interact directly as a developer. This layer is subjected for the ossification, and the releases which we will have after this one, like 0.11 and so on, will happen on the layers above. Changes in the RGB core and new releases there will be happening only with the fast forwards or bug fixes, and they don't expect, probably they will happen once a half a year, gradually moving to the ossification. On top of the core library, we have a standard library, which is the lowest level library, non-consensus library, and it actually adds all the functionality that is required for the applications, but which is not part of the consensus logic. Am I still online?
Yes,
because
all good.
My computer seems to be hanging.
All fine.
I can't do anything to the presentation. It's hung.
You can reload. We can wait.
Yeah, just 1 second.
No.
Sorry, I need to reboot because my computer completely hung.
Sure.
So
take your time.
I will be out for 1 or 2 minutes.
Sure, no problem. Answering the question from the chat, no, we have not yet reached that part. So we have not reached the part where Maxim would talk about the global state and all other details concerning the global state. So stay tuned, stay with us. Hopefully Maxim will come back pretty fast.
Or is it possible to see previous presentation?
We have a YouTube channel where all the information is being posted constantly. With regards to video materials, then we have a GitHub repository with all the PDFs that Maxim presents, and we have a GitHub repository with the audio files from every dev call that we are holding.
If possible, may you share the YouTube channel?
Sure. Are you in any of our groups also, if I may ask? Telegram, Twitter.
Not sure.
Telegram, Twitter.
Only in the Bitcoin Kyiv.
Okay. Yeah, I'll share everything just a sec. I just sent the link to our YouTube channel here in the chat, and in every video you have the description of it, and in every description there are links to our Telegram chats, to our presentation slides, and most of the information that you probably need. So check that link, like, subscribe.
Okay, thanks.
Yeah, no problem.
Okay, anyway, so I was saying that the standard library, the RGB standard library, is the lowest level, which adds the non-consensus functionality, but still the functionality without which it's really hard to use anything related to RGB because it's too low level and it's just an adapter. And this adapter actually has the most of the code because it creates the concepts such as a container, the consignments, the contracts, the contract state, and so on and so forth. And actually, no, I don't expect any software to use the RGB standard library directly. So it also doesn't have any functionality which is specific to Bitcoin wallet functionality. And this functionality is delivered with a library on top, which I called RGB Wallet Library. And these two libraries, they are part of the same repository. I will be showing you how now these libraries are structured in the GitHub. And we have this RGB Wallet repository, which has both RGB Standard library and RGB Wallet library. And what RGB Wallet library adds on top of the standard library are the PSBT operations and ability to filter the contract state which is specific to a certain wallet defined by a wallet descriptor. And that actually was the thing which made use of RGB really hard, because RGB contract, it doesn't know anything who owns some specific UTXOs, and it just reports all of that. And the wallet was always needed to filter which of these UTXOs are related to the wallet and the user, owned by the user, from all the rest of the UTXOs. Now this became part of RGB Wallet library. The reason why RGB Wallet is separated from RGB Standard library is because there might be a different implementations of that logic. For instance, somebody would like to use not a descriptor format, but either format for the wallets, or maybe there could be exchanges which have their own custom software stack. And in that case, they will be integrating to the RGB Standard library through their own custom libraries. Otherwise, we expect that the rest of the software, mobile, desktop, and WASM, will use this wallet library, and it will be the main point of the integration. For WASM, actually, and web browser, they will work directly with RGB Wallet library. At this level, let me show you this another divider. At this level, there is no file system or anything that can prevent applications from working with WASM. No file system, no networking, so this is no standard environment which can actually work with the hardware wallets as well. So the hardware wallets will be working with RGB Wallet library, and it will also have a non-standard no STD version, meaning that it would compile without the Rust standard library and without input-output. Next, on top of RGB Wallet library, there is a new library called just simply RGB, because RGB is used in the Rust world already by a different crate related to the colors, as you can imagine. The name of the crate is RGB contracts. And the idea is that the end users should be able to type a very simple command like carbo install RGB contracts, and they will get everything needed to work with smart contracts, RGB smart contracts. So RGB library will provide also a command line tool called RGB, and it would be the library with which desktop and mobile will integrate. And RGB library adds the file system operations and data storage on top of RGB Wallet. And finally, there is still an RGB node, which we are not releasing this month. The work on it will be happening later, and which will be used only in the server-side environments. And also when a user would like to work with a Lightning network and always have a node that is online, that would be the use case for the RGB node. So it will be called the same, it will be installed in the same way, but it wouldn't be required for mobiles to be embedded into the application. So that is the new library stack, and this is the new structure of the Git repositories in GitHub. The RGB is the first one, is this repository that provides the command line tool and the main integration point. So if you are writing something to RGB, your point to start working with RGB should be this library. Then there is RGB node for server-side setups, RGB wallet for mobiles and desktop wallets to be integrated with, an RGB Core library, which is a consensus level library. Probably you don't need to use it unless you are a developer of RGB Core itself. Then there is a black paper, which is a work in progress on RGB white paper, and repositories related to the contractum language, which is still an early stage development of RGB, of a language for RGB smart contracts. Before it's released, you still can write RGB smart contracts, and I will be showing today how to write RGB smart contracts without the contracting language in Rust. But of course, with the contracting language, it will become more elegant and simple. So last month, we released RGB Core libraries, and we described in details how they work. Today, I will be touching RGB Standard library and the main RGB library on top of that. Next week, I will move to the RGB wallet library. And the idea of this new RGB library is that we should have one command to rule all RGB contracts. So instead, some complex workflows like we had with the previous versions, where we had to write a bash scripts lasting many 100 lines of bash script code, with the version 0.10, we should just move to a use of a single command. So the user should be able to do just cargo install RGB with all the features, and then do all smart contract operations, like see what contracts it has, issue an asset, check the contract state, check a contract state in context of a certain wallet descriptor, and of course do asset transfer, accept asset transfer, verify them, and do everything like that. No need to install multiple tools, and just a single command. The design of this RGB command was inspired by the idea that actually we should have something like Git. With a single command, a Git manages a lot of, well, not client-side validation data, but still the data kept by the client. Git doesn't have anything related to the blockchain. But like RGB, it has a lot related to the local storage of the data, which must not be lost and which also can be transferred between peers. And pretty much the same applies for the RGB. So RGB command should be the command that actually opens the world of RGB smart contracts to the end users. And of course, if you are doing a mobile wallet or desktop wallet, you wouldn't be using this command, but you will be using a library behind this command, probably through C bindings if you are not writing in Rust. And this library will be called librgb as libgit. And basically it would be something similar to that. This RGB tool, I was planning to do a demo today of using the RGB tool, but still there is some tasks which are not completed, so probably this demo will be moved to the next call. And today I will be showing how to use the RGB functionality from the RGB library itself without the command line tool. I mean, it's just about completing the command interface for the command line. So to start working with RGB contracts and interfaces from the code, we need to understand some core concept about its anatomy. And that's what I will try to do in the next part of this presentation. So first of all, RGB contract state. There are two main kinds. Any RGB contract has two main kinds or two main forms of the contract state: global state and own state. And the difference between them is very simple. Global state is the state which nobody owns, but everybody knows. And own state is the state that someone owns, but nobody else knows. So they are just opposites of each other. An example of a global contract state is the name of an asset that you issue, a ticker of an asset, a contract which is bound to the asset itself and in terms and conditions. It could also be some form of general publicly available information. Or, for instance, if you are doing complex forms of smart contracts, you may include some pre-signed Bitcoin transactions which can be accessed by everybody and so on and so forth. The own state is the state, the example of own state, for instance, is the amount of asset you own on your wallet, or certain forms of rights, like rights to vote, or rights to do a secondary issue of the asset, or rights to issue additional items of NFT collection, or NFT content itself, something that is bound to a specific user and something that can be performed only by that user. The state, the own state, can be updated, changed only by the user that controls certain UTXO. So that's the difference between these two main things of the state. And this makes RGB quite different to all other smart contracts things, because I don't see that there is clear distinctions between these two types of the state in any other smart contract platform. And own state can have four main forms. The first form is the declarative, where it's actually no state attached to the UTXO. It's just a right to do something. For instance, a right to rename the asset, or a right to vote, or a right to do the secondary issues. So basically, it's a form of governance related to the smart contract. The second type of own state is fungible state, which is always hidden behind zero knowledge with the Pedersen commitments. And this is some amount that can be fungible, that is fungible with other amounts. So usually you use the state to specify the asset amount. The third type of the state are the structured data. And this data, which can have arbitrary internal structure, they are using the strict typed system. And for instance, if you're like right now, we don't have a direct examples of this structured data, but in the future, for instance, when we will do a digital identity smart contracts, that could be a public key plus certificate over the public key stored as part of the contract state. Then we have an attachments, very useful for NFTs, and attachments are not directly transferred with the contract always, because they can have a different size, a very large size, gigabytes of the data, but they will be made available through an independent networks like Storm, or via Lightning Network, or via Torrent, and the contract specifies the means to access that attachments, and also specifies the type of the meme type of the attachment. So that's the contract state. And quite important question I would like to touch, and there was actually I've seen that there are people who are interested in this specific problem. In RGB, do we have a global state accessible to all the members? Because we don't store the state in the blockchain. We don't store the state in the blocks. How it is accessible? Well, it is accessible because it is published to a distributed data networks, or kept on some centralized servers, or both of that. And the parties which are doing this are the creators of the contracts, the issuers of the contracts, or the participants of the contracts. And why we think that this is sufficient to provide the global state accessibility? Well, because if you think about how the Bitcoin blockchain works, this is exactly the same mechanism. Because in Bitcoin blockchain, you don't have a guarantee that the blocks are kept forever. For instance, many Bitcoin nodes, they prune the history, and they keep only the historical data which are related to the UTXO set they are interested in. And the only reason why you still can download the past block history of the block is because their Bitcoin P2P network provides this information for free in expense of the account of the Bitcoin holders and miners, which just understand that this data are the common good. So there is nothing in Bitcoin consensus that guarantees that the block history will be kept forever. Even more, with the zero knowledge rollups, which may come, not rollups, but with the zero knowledge proofs, which may compress the historical data in the Bitcoin blockchain, we will lose the historical blocks eventually, and this data wouldn't be available forever. So I'm trying to say that Arguably, keeping the data in the distributed networks in the centralized servers where the parties interested in the availability of this data are paying for the storage directly, not relying on the common good, is actually gives a stronger guarantees about the preservation of the global state than the block storage. And the same applies for the availability, because basically RGB doesn't know which specific data storage layer you are using. But for instance, you can always, as a contract creator or a contract user, you can always stick to some layer that requires the user to pay for requesting certain information through the Lightning Network, for instance. And that's why the nodes in the Lightning Network will be incentivized to keep this information, because it will create an additional revenue stream for them to provide this information to the consumers. Or it could be a different setup, that the contract creator pays to the nodes to store the information such that users can retrieve this information free of charge. So it will be completely up to the contract developers to develop and build an incentivization model into the contract. And this incentivization model, if present, will provide a better guarantees than the storing the data in the blockchain itself. And at the same time, it will also be much more scalable than storing the data in the blockchain. So that's why we assume that the state will be globally accessible and available. And in RGB, you always know when you receive the consignment, when you receive some certain form of transfer, it also, I need to note that it always comes with the all global state required for the validation. So it wouldn't be, there wouldn't be a situation that you receive the consignment and you can't validate it because you don't have some data and you need to talk to the torrent or to the Lightning Network. No, it's not the way it works. When you validate the data, you have all the data, including the global state. It is only the case if something else in the network has happened, which are directly unrelated to your assets, such that you need to ask for that additional global state as an owner of an asset. Let me provide you an example. For instance, you own certain company shares and you own them locally with RGB smart contract, you validated them, and your ownership is not distorted by any external events. But the company may have a right of the secondary issue. They can inflate the supply of shares. And it is the part of the contract conditions which you have accepted. And when they do a secondary issuance, they spend a specific UTXO, which you know from your data. And you can detect the event of that this UTXO was spent, so you will always know that the shares were inflated. The only thing that you don't know that how much shares were created. And to access this information about how much shares was created, you need to talk either to the company centralized server and ask them for this additional information, or the company may publish this information into a decentralized network like Lightning Network, and you can access it through it. It will be up to a specific contract to decide how specifically structured this. But again, the inflation of the asset, it affects you as an owner of the asset, but in an indirect way. And it doesn't affect the validation of the asset. So you still can transfer the asset further even without knowing this global state data. So even if the global state data are not available through the decentralized or centralized provider, the RGB smart contracts can still operate and validate. The only case where you need additional global state data is where you build some non-trivial, non-linear scenarios when you would like to build the validation of a contract on some certain global events. And in that case, you will use the decentralized networks and it will be possible. And I expect that even in this case, the availability of the data, the guarantees of the data availability will be same or higher as with storing them in Bitcoin blockchain. Because it's quite important task, maybe you have questions regarding that before we move to the next slides.
Yeah, I would have a question about the incentive. So if I buy for example, a company share, how is that the main incentive to keep it available should be a burden of the contract creator. Isn't my interest as well to guarantee availability of the data? So I don't really understand. Yeah.
So basically, there are multiple parties. Usually, there will be multiple parties. All contract participants will be interested in guaranteeing the availability. So they may, like in Bitcoin, provide this information by default. For instance, they can all run the Lightning node and publish this information through the Lightning network, through the Lightning node, or they can come together and decide some other options of how they make data always available.
Okay, so it's not the contract creator alone that is incentivized. It could be him or eventually any single token user.
For instance, if I'm a shitcoin creator and I grabbed 100 millions for my shitcoin, then probably I will be the party which will be paying for making the data available. And I wouldn't be asking, well, shitcoiners would be, but probably some of them wouldn't be asking users to also pay for the data availability. But if I'm like sincere guy who just does something, does some startup, a company, and issues shares to its investors, I think it would be our common interest in keeping some global data available.
Just an input to that, or an idea. And in future, it might also be that third parties would be interested in providing the data for a fee, so that if you lost your contract, you can just buy it from someone who owns it on his network.
Absolutely, and that's the idea of the Storm network, which runs on top of Lightning, and where you can, for instance, I'm running the Lightning node, and I see that there is a demand for certain information. I publish this information on my Lightning node through the Storm, and I'm getting paid for each request that comes to me with the Lightning fees. And that's why if the users are interested in certain global state, for instance, there are designs we are working on of algorithmic stablecoin or synthetic stablecoin, collateral-based stablecoin, where the global state is quite important for the operations. And or you can have some DLC-related applications where a global state is related to the DLC, has to be available. And in this case, users will be prepared for paying for that global state availability. And the Lightning network can operate as a data network, providing the information about the state for a fee, which is impossible with any other existing smart contract platform, where you can't just pay for certain information. It's always either embedded in the blockchain or it is stored somewhere where you don't have a proper incentivization structure. Even for Bitcoin blockchain, I think that there is no proper incentivization structure for keeping the historical blocks. Not saying about IPFS, torrent, and all other types.
There are a couple of other questions in the chat. So the first question is, so the global state is basically the contract metadata? And if yes, then probably the global state is a bit misleading. Can you comment on that?
The global state includes, so the contract metadata, of course, a global state. But there could be different forms of global states which are not just the contract metadata, which are created by the contract users and which may be requested by other contract users, and it's not per se contract metadata.
Okay, I hope that.
For instance, if you run a global domain name system and ENS analog, the domain names, certain forms of information related to domain names would be a global state. And it's not just a contract metadata, it is a state of the contract.
Okay, makes sense.
And also regarding the metadata, we have in each contract operation have a metadata which is not the same as the state data. This metadata is additional information which is required for the validation of this specific information, and it is not a part of the contract. And you can think about this metadata of the operation as a witness stack of the Bitcoin transaction. And if I will use the metadata for the global state, it would be really hard to differentiate that with the metadata of the operation. So we actually was selecting the name for the global state for about 2 years. It was unowned state, public state, open state. We tried all the metadata, all these terms, and finally we stick to the global state because it's like, well, it seems that it is the least misleading among all of that.
And thanks. And there's another question. What about using ordinals inscription, like storage to store minimal global state?
I don't see, like, it has a lot of drawbacks and no single reason to do that.
Added value.
Like, sorry?
No added value.
Yeah, no added value.
And it's not scalable whatsoever. So.
Yeah.
Okay, cool. I think any more questions? We can move.
Yeah, let's move forward because we still have a lot of information to discuss.
Sure.
So both global and own state can be structured, and it can be transformed into JSON, YAML, TOML, or other data formats, such that, for instance, when you ask the RGB about smart contract state from a software, from a wallet, you get the whole state, including the structured data converted into YAML string or JSON string, such that you can parse. And you, as a wallet developer, don't need to stick to a specific, you don't need to know about the contract data, about the data contract operates. You still always be able to look into this data because they are transferred in some interchangeable format. And it also, as I said, it's inspectable through the Alluvium opcode, such that contract logic can use the global state or own state data to run some custom validation of arbitrary type. The next thing I would like to mention a term assignment, which is also important to understand. And assignment is when you get an own state and assign it to certain UTXO. So own state is just a state data. And when you bind it to a certain seal, single use seal definition, which is a UTXO, you create an assignment. So assignment means basically the own state plus some UTXO in a very simple terms. And the state validated, how the state is validated, both global and own state. The global and own state validated in 2 layers. The first layer is certain declarative rules, and these declarative rules define that, for instance, of which type the state should be. And if there is a state which is realized as a binary string, when you try to deserialize and it doesn't match the type, it basically fails the validation of the smart contract. And there are other rules, like how many items of the global state can exist. So each state operation, each contract operation can bring new global state values. And these global state values can accumulate over the time. And there are rules which are part of RGB contract schema that say that the global state shouldn't accumulate for more than a certain amount of items. For instance, if you're talking about the asset, and the asset can be renamed, you also specify that the global state of the asset name do not accumulate more than 1 item. So there is only a single name of the asset, and the history of the asset renaming still will be accessible, but not treated as a part of the contract state consensus data. And all these declarative rules are coming as a part of RGB schema I will be talking about later. And there is also a custom script logic which can also be used to validate the state, to do more complex validation. For instance, if you just don't need to be sure that the state is of certain type, but also to put additional restrictions on what state means. For instance, make sure that the transaction ID referenced in the operation is actually part of the mine transaction. You can use Alluvium virtual machine and do this inspection logic through the Alluvium virtual machine. And it will be also a part of the state validation. So here we're coming to the RGB contract schema. What it does, the RGB contract schema is actually a declaration, it's a declarative thing, which defines which type of state can exist. They also specify which specific data types used for constructing that state. which operations can be performed with a contract and which state is modified and updated by the operations, and how these operations can be constructed into the graph. So all these rules are the part of RGB schema, and in a moment I will move to the actual code to show how they are looking like. And why the schema is important is because it helps to differentiate contract developers from the contract issuers. And the contract issuers do not need to know anything about writing programs, writing contracts. They're just creating an asset based on a certain schema created by the professional developers. And schema is basically a contract template, which can be used in issuing multiple contracts. Because, for instance, if you are doing certain form of token, you don't need to write a new contract over and over again. You just use certain existing template, which is the schema. So here is how this contract schema is looking like. 1 second, I need to switch the screen. It's really hard to do that. So what about the screen size?
It's fine.
Sorry?
It's fine.
Fine, okay. So here the code written in Rust, which creates an RGB contract schema. You also can do that with a non-Rust code, and the next week I will be showing you how you can actually compile some non-Rust schema definition. For instance, here I created the schema definition with a TOML file. So that's the same declaration matching exactly the Rust code. And in the future, with the contraction, you will also have ability to write the schema in much more simple format than this quite elaborative structure. But right now, probably the simplest form for developers to start with the schema will be to using a Rust. And you start writing the schema by starting with the defining constants for the state types. So you say that, for instance, you're issuing an asset, and this is a simple schema for a token. You say that the asset has a name and precision and all that information, which we call a nominal of the asset. It also has certain terms and conditions, which we call a contract. There will be an operator. So these two are global state. GS means the global state. And it's just an integer. You assign arbitrary integer just to differentiate them from each other. And there is also an operation of the contract, which own state, which is actually a state of the amount of the asset you own, and an operation of transferring the assets. So you create these identifiers. And then basically inside the schema, which is just a structure, you define the global type and own types. And this global types is the mapping between the type identifier and the type name. So you're using predefined type, and you also specify how many times this item may appear in the global state. As I said, because we are using an asset which just have one name, and if you rename the asset, only the latest name is actual valid name, we specify that through this once type of declaration. And the same for the own type. You create a fungible type of the state, which should be a 64-bit integer number. So this is basically the way how you define the contract state. Now, where these types are coming from? They're also coming from Rust. Let me show how it works. So the types is the certain standard types which are provided by the standard library, RGB Standard library. And if you look into the standard types thing, it's basically it takes a lib builder. This thing comes from the strict type system. It declares the library name, and then it compiles the Rust types into this library. And then it links multiple libraries together. Here it's just one library, but in the future there will be more. and exports this linked strict type system into the RGB. So what is this nominal, for instance? The nominal is the Rust structure, which has a ticker, name, details, and precision. And the way how you can make this nominal structure available to the RGB is just by writing these two derivation macros. That's it. And then you can compile any Rust type into the RGB code. And if you look into the precision, for instance, it's quite interesting because it's an enum, not just specifying the number of decimal digits, but also providing a verbatim name for them. And this name will be kept inside the RGB schema and available to the user such that it will represent a part of the semantics which are kept in the RGB contract. So you can also do that. You can also compile this type into the library. And the real library which is compiled from this is it's just not the, here you see, we compile two types, nominal and contract text. But in reality, it takes all the types which are used by these types down to the primitives and make them all part of the single library. So when we look into the library, it will contain all type definitions. And let me show you how the type library is actually looking. If I will open the RGB Core thing, and probably the window hasn't switched, right? You don't see the library.
Nope, it's still on the same part.
Just 1 second, give me 1 second. You see now, right? In each repository, I have this STL, which is a strict type library thing. And here you see, for instance, the way how the compiled types are looking like. This is a type library compiled from RGB Core. It's a representation of RGB Core type system as a part of the strict type system. So you see a lot of type definitions, which are all created just from importing a single data type. And there is also a binary format of the same library. Of course, we can't use it. We'll see it in the text editor, but I can print it out in the command line, which is the compiled version of the same library, containing all the semantic information inside of it. So that's how the strict type system is working. And that's how the types are imported into the RGB data types, custom data types. And so we are using this type library from standard types, but nothing prevents you from importing any custom data type. And then you use this type name coming from the Rust type name plus the library name to import it into the global types or own type system. So that's the first part of the definition of the schema. The other thing that you do inside the schema, you define the genesis. And genesis actually is a specification which data has to be provided at the contract creation. So which of the global type and assignments has to be created together with the contract. And it basically references the same type ID plus provides amount of data which can be made part of the initial contract state. And again, we are creating just one asset name and one asset contract, but we can create a multiple asset assignments. So one or more asset assignments can be part of the genesis state. And the final thing that, not the final thing, but the next thing that we are doing is we define the state transitions. There is only one state transition type, and this state transition type can take as input any previous assets, one or more, and create a new assignments for assets, again, one or more. But how we make sure that the amount of assets we are spending is the same as amount of assets getting to the new beneficiaries? This is done with a validation script. We create a Alluvium script. We also reference Alluvium libraries, and I will show you how the library system works for Alluvium. So you can have some libraries written by independent developers, which will be reused in multiple schema and multiple contracts. And you can use multiple libraries as well. And finally, you specify the entry points into the scripts. And these entry points are specific to the validation procedure. There are certain validation procedures like validate genesis, validate specific state transition as a whole, or validate specific global state or own state data. And here we don't need to validate anything because everything else is specified as a schema. We don't need to put additional constraints, except the validation of the own states regarding to the assets. And with that, we call the library function. And this library is actually the library we've written here. The code of this library is a single instruction. This instruction is validate Pedersen commitments of the type for the own state of the type of the asset. The sum of inputs is equal to the sum of outputs. This is a single Alluvium procedure we are putting into the code base. We compile this code base and then we add it as a library to the schema. And this gives us the first schema, which can be compiled and run through the executing this program. And let me just do it right now. Well, here it is. The first part of this output is the compiled RGB schema with this identifier. And this schema contains all the source code of the Alluvium, of this type system, and everything else inside of it. So that's the schema. Let's move back to the presentation. But this is not the end of the story. We have now a schema with all this new type system and everything. We wrote something really custom, let's assume. And there is a wallet. There is a wallet which the user of which has imported 3 different smart contracts, A, B, C, D. One is the contract for a fungible asset, another is an NFT collection, the third one is a DAO with many identities, and maybe a contract which also issues 2 tokens of different type plus some NFTs, so some advanced functionality. And the wallet just don't give any clue how to present the state of those contracts, all these custom contracts, to the user interface and how to interact with them. So that's a real problem. And that's the problem we address with the introduction of the interface system. So without interfaces, we were not able to unlock the potential of complex smart contracts because we were restricted to a very few types which would be understood by all the wallets. But with the interface, the wallet would be able to interact with these smart contracts by using these interfaces. So interface is a human and wallet readable information about the contract. Information about the contract state and contract operations. And interfaces help to make sense of different contracts for the users or for the software. They tell about a semantics of the contracts, what state the contract can have and how to read parse it, what operations can be performed on the contract, which arguments these operations take, such that a different smart contracts implementing different business, implementing the same semantics of business logic, like a fungible asset, in a very different way, can still expose this business logic through the same unified interface. So how to understand better the difference between contract and interface. If a contract is a class in terms of objective-oriented languages, interface is the interface of that class. And in Ethereum world, interface is basically an ERC standard. ERC 20 standard is the interface of Ethereum contracts. In the same way, RGB20 interface is the interface of RGB contracts. And the interface, but in Ethereum, you don't have a compiled interface. It's just a written standard. In LNPBP world, in RGB, our interface is actually also a compiled program, which exists in binary or base 64 encoded form. And a contract may implement many interfaces to deliver advanced functionality. So for instance, a single contract can expose NFT, fungible assets, identities, or some other forms of interfaces. And interfaces unlocks a way for independent developers to write any kind of contract and users to use them without additional RGB libraries, wallet software updates. So if you create a new interface, you release it, users can import it, and they don't need to update the wallet. And the wallet will be able to work with the smart contracts through this interface. Interface consists of mappings between human-readable names for the state data and human-readable names for the operations, and the actual data types which should be behind them. And when the schema implements interface, they need to make sure that they use the same data type, and they map the type ID, which we just created in our schema creation, to the name of the type defined by the interface. So let's see how it works in practice. Again, I need to switch the screen. Here we are. We define the interface. Oh, sorry. Oh, here I need a different window.
It seems that your computer is about to fly off.
I think I will abandon using my MacBook at all. Never will. It's just absolute piece of crap.
Is this MacBook?
Yes. Pro. 1 second. So you see my screen, right?
Yes.
The standard library defines a number of interfaces, and this is an example of RGB20 interface defined by it. And the interface is written pretty much in the same way like the schema, with the difference that here we have the names for the state, and we map these names to the state types, also with some additional requirements on the number of attempts can happen. On the number of times this item can happen. So we do the same for global state, own state, for genesis, for state transition involving the state transfer. So this is the way we write the interface. And when we have this interface, we do implement the interface for a specific schema. Here we are. We're doing interface implementation. We're specifying a schema that we wrote just above. We're specifying interface, and then this time it comes from the standard library. Here, this method defining this interface in the standard library. And we create a bindings between these type IDs we created for the schema and the names which are coming with the interface. And then the compiler takes the rest of the story. So we write the schema, we create this interface, and when we create the interface implementation and when we import it into the contract builder, it compiles them all together and verifies them against each other. But we will get to that in a moment later. Now I will be switching back to the presentation. So right now there are 5 interfaces which will be shipped with the standard library. The first one, RGB 20, is for fungible assets like company shares or shitcoins. RGB 21 for digital collectibles like NFTs, books, musics, or some shitposts and stupid memes like with the ordinals, but without wasting block space. RGB 22 for digital identity. RGB 23 for provable history of operations. It's like open timestamps, but where you just not commit to a single thing, but you commit to a history of events over the time, and you can't modify this history back in time. And finally, RGB 24 for global domain name system, like ENS, but much better. These interfaces are created by LNPBP Standards Association, and they are part of the standard library, but it's not that nobody else can do an interface. Anybody is open to create new interfaces, publish them, and use them in their smart contracts. It's just a thing to start the use of RGB and simplify the life of the developers. So RGB contract is a schema, which we already get into, and the schema is the requirements for the contract state and contract business logic. You can compare a schema to a class in terms of objective-oriented programming, plus an implementation of certain interface, and this implementation binds the schema raw data to the human and wallet readable names, and a genesis, which provides initial setup of the contract state. And here I put this into a table form to get it more understandable. So we have these 4 contract components: interface, schema, interface implementation, and genesis. And they have their own meaning. So interface is the contract semantics. Schema is the contract business logic. Interface implementation is the mapping semantics to business logic. And genesis is the initial state of the smart contract. I also provided terms from the objective-oriented programming, which may help to understand better how they interrelate, and also from Ethereum world. So in this case, the Ethereum contract is basically what we call schema, and the interface is the ERC standard, while interface implementation is the EBI, which is shipped with each contract, and genesis is the contract constructor. So how we do put all these things together and finally issue an asset. Here we go. We use a thing called contract builder coming from the standard library. It's a builder interface. You initialize this builder interface with a certain interface, again, from standard library, it's RGB 20 in this case, with a schema we just wrote, and with the implementation of this interface for that schema, which we also just wrote. Then we specify the chain on which the contract operates. In this case, it's a testnet. And we're starting adding a state to the genesis. We're adding global state, the nominal of the asset, from the variable we just wrote. Here we're creating new nominal test ticker, test asset name, and we specify precision, which is centimicro, the same as in Bitcoin. Then you add a fungible state, which is an assets. You assign this asset to a beneficiary, which is specific transaction out point, and you specify amount of the assets, 1 million of assets plus these numbers, like in Satoshis, we need to add more decimals. And finally, we do an issue contract, and that gives us the contract. And this contract has an ID, and we can ship this contract. I will be explaining what Bindle means in a moment of time, and save it into a file. When I run this thing, I also print all the information. So this is the schema we just created, and it can be sent over the network and imported into different RGB stashes. There is interface implementation, which is quite short. There is RGB contract, which we just created with them through this contract builder. an asset we issued. And we can query the state of this contract here. The final part of the story. We have a contract here. This is the contract. Then we create a stock. The stock is in-memory representation of the database that stores RGB data. It's quite useful for WASM, so you can do that right inside the browser. You create a stock, you import into the stock interface schema in the interface implementation such that it would know it. Then you take the contract that we just created, we do the validate procedure, we run the verification of the contract and make sure that it is valid. We import this contract into the stock, and then we can interact with this contract through the interface. We call this contract interface for the contract ID. We're using RGB20 interface. And this creates an object with which we can talk to and ask about the state or perform some operations. So here we are reading the global state of the nominal and the fungible state of the asset and print them out. And we'll see that basically that's what we are getting here. We are reading the contract state of the asset we created from this contract above, including the precision, which is now mapped to the integer 8-digit precision, and the amount of assets we all issued and assigned to the UTXO. So that's how basically any wallet will be interacting with RGB through this API of the standard library, which allows you to create schema, to use interfaces, to do contract verification, to issue the contracts, and to interact with the contract state through the API calls. Another important thing which I would like to mention is that the only way how you can import the contract is by using the verified contract procedure first. So here, when I run this thing, see that it works correctly. If I remove this verification of the contract and instead import unverified contract, not validated. So unvalidated contract can't be imported into the stock. You need to run the validation procedure, and the validation procedure have to succeed. And you can also inspect the different messages that comes from validation, because there are warnings, there are certain informational messages, which can also be inspected by the wallet and taken into account by the wallet. If you look into the details of what contract is, you will see that there is a validation status field in the contract, which contains the validation status composed of these failures, warnings, infos, and so on and so forth. So that's the way how you interact with the RGB in programmatic way. RGB command line tool basically does all the same, but it wraps this into just command line calls, plus it adds a storage. So instead of using the stock, it has a more advanced file system object that stores all this data you import on the file system. Now back to the presentation. We are really close to finish. Now, how we have this contract, how we will work and redistribute this data. There are two main things to keep in mind about the sending data between the peers. The first thing is the consignments. You already heard about them. If you used RGB before, and the consignment contains full information about the contract and contract state required to perform the validation. There are two main types of consignments: contract consignment, or simply contract. If you issue a contract and you would like to let people know about your contract, you create this contract consignment and publish it. And this is the contract consignment we just created. You see, like it looks like this in base 46 encoding format, and you can copy this data and send it through the Telegram, email, or wherever way you want. Or you can use the binary file as an attachment. or you can publish this binary data into the Storm network. So there are many ways how you can distribute the contract or any consignment. The second type of consignment is transfer consignment. It's used when you send assets to some other party or when you interact through the contract with some other party. And this consignment are pretty much the same. They are just different in their purpose. The second type of data structure you are using when you do a peer-to-peer interactions in RGB is bindles. It's not bundles, it's bindles. The bindle is just a small bag behind the back of somebody. So I choose this name to identify these pieces of information. A bindle is an RGB item plus some additional signatures. And Bindle, you can wrap into Bindle RGB schema, RGB interface implementation, or the consignment itself. And you can also sign this with the developer signatures who created the schema contract or with the issuer of the contract signatures, such that consumers can also check these signatures. And these representations are actually a bindle. So it's a consignment or schema wrapped into the bindle and serialized in a binary or base 64 encoded form. And then it can be deserialized back on the other part, on the receiving side. All these bindles and contracts and schema, they have their identifiers. And if and I would like to show that to you how it works. If I open this is the RGB command line tool I was talking about. And here are an example of how it works. So if I just run the RGB command, first I need to do a build. You see we're compiling Alluvium and all the libraries related to single-use seals, then RGB Core, Standard library, Wallet library, Contracts library, and finally the RGB binary. So when we run it, we are able to list the contracts which are known to the library. And right now we don't have any contracts known to the library, but if we will import, we will see this. No, okay, sorry, I haven't imported this from my other machine, so I can't show this part. But what I can show is how the contract definition for the contract creation based on certain schema will work in Contractum language. So you can define the nominal contract text and assets in quite a simple and short form. And before the Contractum is released, you will be able to issue the contracts based on YAML, TOML, or JSON representation of the contract by just running RGB issue command and providing this file, this source file. So that's the way how this contract issuance and creation will work from the command line. Finally, back to the last slides of the presentation. The identities. The identifiers we are using for identifying contracts are so-called Baid 58 encoding. It's an encoding we introduced in LNPBP quite recently. And we decided if you were working with RGB before, you were seeing that we were using BAC32 based encodings. And we decided to abandon them because due to a number of reasons. First of all, they're quite long. The second, BAC32 is a bit misleading in the promises it gives, like it is QR friendly, it is easy to read, and it does the error correction. Nothing of that is true. So the QR encoded BAC32 string is not, it actually produces a larger QR code than base 60x 58 encoded string. It is also not easy to check because people just don't know that they need to verify in the BAC32 string these last characters. They're usually looking into initial characters, which provides very poor guarantees of the correctness of the code. And it's really easy to misinterpret the actual string. In Baid 68, we put this mnemonic of the checksum of the identifier as a human readable thing, which will help people to see which specific contract and ID they are using. It's much better than BAC32. And it also, the error correction with the BAC32 is not working as expected because it is expected to correct if some characters were misspelled. But actually, it is not advisable to do this. No software implements this autocorrection, and the idea that wallet can autocorrect. But in reality, the users, if some of the characters were misspelled, the user should not use that string at all and should not use that address at all. So these are BAC32 things, promises are not advanced things, but actually not things that work. And the reality that BAC32 strings are much longer than base 58 encoded strings. So for RGB identifiers, we fail back to the original Bitcoin address format, which is base 58. Plus, we enhanced it with a readable mnemonic in front in form of the human readable prefix. And we hope that will make work with RGB contracts simpler. Final notes, how to keep the data, RGB data, and back them up. There are two main terms. The stash is all consensus critical client validated data in their original form, which must be kept and must be backed. If you lose the stash data, you will lose the assets you own and you will lose the state you own. And they are not accessed or used directly. It's more like a storage of everything you need. And you use this data when you create a new state transfer to create the consignment. Another thing is the inventory. The inventory are the derivatives from the stash, and they simplify the access to the current contract state. They include different indexes, and you're not required to back them up. But it is advised to back them up because to regenerate it from stash, you can always regenerate the current contract state from the stash, but it's a very complicated procedure which is not yet implemented. So for now, it is advised to back up both stash and inventory. And both of them are stored in these locations. So if you use an RGB, if you just run the cargo install RGB and start using the smart contracts, all the stash and inventory will be residing in these repositories. And these repositories which has to be backed up, including the mobile version of these directories. Inside of this directory, you will see a mainnet, testnet, and so on. And inside of that right now, there is just a single file, but later on we will move to a more advanced directory structure. So that's all for today's presentation. We explained what RGB smart contracts are, what is the anatomy of them, what is interfaces, how to do smart contracts interfaces, schema, and how to issue the assets. We also explained what comes with a version 0.10. And next week, we will continue to the wallet functionality and state transfers, how to transfer the assets, how to create PSBT, how to add RGB information into PSBT files, and how to accept the transfers coming from the remote parties. Also, so with that, hopefully the road to release of RGB 0.10 will be completed. And what's next after that? We will work through the spring and summer on the Lightning Network operations and on the nodes, which will work all together in context of the Lightning Network, RGB node, LNP node, and Storm node for the data network operations. And this will include the development of the DEX, because basically the Lightning, RGB Lightning parts of the protocol, they will be DEX aware, and that would be basically the same protocol by its nature. So hopefully by the end of summer, we will have the RGB assets transferable through the Lightning Network. And this autumn, we would also spend time on doing tools for RGB developers, like completing the contractum language, doing the compilers, package managers, different repositories for existing schema, type libraries, and so on and so forth. So that's the roadmap that we have ahead. And it was quite a long call, even though it was split into two parts, and we have gone only through the half of the topic. But next week we will continue. I'm done, and back to Olga. Back to you, Olga.
Thanks, Maxim, for the presentation. It's been really cool. A lot of new words, but also a lot of very good explanations. So, questions. I would probably start with Giacomo and Federico and other guys, because they told me they would need to leave.
Now, I just have a question that I hope is not redundant with the same question I asked already, because I have a little bit of age problem. It's not clear to me the difference between the identity application and the global naming system application. I mean, I can imagine that there is a difference of more ephemeral identity in the first case and more stable long-term, but it still seems like a very similar protocol of like name systems are basically identity systems, if I don't misuse the term.
Yes, thank you for the answer. Actually, well, of course, they are highly interconnected. The difference is that it's two different applications, and parts of its business logic are different. So I will open these two things I wrote before. The RGB interface, now it's called Schema, but it's actually now an interface for decentralized global domains name system. Oh, it's here, sorry. Decentralized global naming, yeah. And if I see the resulting thing, the registry links name to the identities. So the identity exposes one form of interface where you have just a single my identity, and I manage the different keys which are bound to this identity. I do key revocation procedures. This is the standard which we have next to this one. Not naming, no, it's already merged. Reputation and identity interface. Here it is, yes. So we have an email, meta information, photo, which are part of the global state. Plus we have this revocation procedure, renaming procedure, and attestation when you sign one identity with another identity. So this is example of the identity interface of the smart contract. And here is a global name system where there is a registry which binds certain identities to names, and they are composed together. So if you create a contract, you probably, for the name system, you would probably also implement the identities. But there is also a difference between identities, is that identities, they don't have a global contract. I can create my own identity and it's my contract. You create your own identity, it's your contract. It's all different contracts. While the name registry is usually global because it has to link to list all the names which are existed in the registry. And that's why it's different interfaces and different forms of the contracts, while they still in practice will be combinable in certain form. Giacomo, does it answer your question?
Yes, thank you. Thank you very much.
There's a comment from Pantamis. I'm sorry if I'm not stressing correctly your name. The comment is, I think domain name cannot be renamed, while identities are not only about the name.
Can you repeat, please?
So the comment on the current question that we just discussed is that domain name cannot be renamed, while identities are not just about the name.
Correct, yes, I think that's also true.
Okay.
That's a good point.
Mm-hmm. So, further questions. Kier, you rose your hand, or was that a misclick or something?
Yeah, sorry, it was a misclick.
Okay, no worries. Next, the question is, are interfaces mandatory for a contract?
No, but if you don't implement an interface for a contract, the wallet users wouldn't see it. They wouldn't see anything about the contract. Because the interface is the way how the wallet reads the contract, through the interface. Otherwise, wallet has no idea what the contract is doing and what's in there.
Okay, I hope that answers the question. If not, feel free to
It's like, can you have a software, a program that doesn't have a user interface at all? No input, output. Well, you can have, it will be a thing in itself, but the user wouldn't be able to interact with that. So if you can write a contract without interface, and you can write a program, a dedicated program that interacts with that contract, knowing this contract in advance, and run this contract on this program on some server. Yes, this will work. So of course you can create a contract without interface and interact with that. But the normal users, ordinary users, existing wallets, they wouldn't be able. So you need to write a custom software for the contracts without interfaces. That's probably the most precise answer.
Okay, that answered the question. Hivemind?
Yeah, hello guys. Max, amazing presentation. The progress is super huge. One question, these examples that you were showing with the Rust code for doing contracts, is it already available publicly or
Yes.
you're gonna publish it soon? Okay, so
It's
I can...
already available. It's in GitHub, RGB WG, the standard workflow for RGB.
Oh, okay, okay.
RGB SC repository.
Yeah, perfect. Thanks so much. Amazing progress, just like mind-blowing, especially like this simplification for RGB CLI with Git is absolutely beautiful.
Thank you. Thank you. Well, unfortunately, I was planning to complete all of this by the start of March, but I underestimated the amount of changes which was required by this introduction of the interfaces. I had to rewrite the whole standard library, basically, from scratch. Another thing, because the switch to the string types actually also means that all collection types change. Now all collection types which RGB attaches are always confined collections, meaning that there are always guarantees about the size and the number of items in the collection, independent of from the platform hardware platform the program is running on. And it also required to basically rewrite everything because all the base type system has changed. So that's why I'm still in the process of releasing the final libraries with 0.10. What I showed today, it's all working and ready. What is not yet ready is that the command line tool doesn't have this command line interface for all the procedures I demonstrated in the Rust directly. And the wallet operations related to wallet descriptors and PSBT are not completed. And I hope to complete this by the next presentation. With that, it will be a RGB 0.10 release.
Nice. Well, to be completely fair, it's only the 9th of March, so if your schedule was to have this prepared 9 days ago, it's not too bad. It's not even 2 weeks, right? So it's pretty cool.
Well, we're still not there, so let's get it done by the next week.
Okay. Next question is, so I will rephrase it. Maxim, can you please walk us through the process of verification of the global state once again? Because there's a question like, how can you be sure that you have the last version of the global state, because you don't own it, you don't see it, you see it, but you don't own it.
Yeah. The idea is that you always know, do you have a last version or not last version of the global state? Because the global state is updated with state transitions. And state transitions are always created when you span some of existing UTX source. And in Schema, you define which state transition can change which global state. So by looking at the contract, you are able to analyze, do you have all global state information that is actual or not? And also, you need to understand that you have always a partial view of the smart contract. The validity of the smart contract is not a global thing. The validity of smart contract is a personal thing. It is not contradictory, meaning that all parties owning parts of the smart contracts, if all of these parties are valid, the smart contract also valid. But it could be that some parts of the history of the smart contract are invalid, and that wouldn't invalidate the other parts of the history of the smart contract. It's really up to the point that when you validate the smart contract, you are interested only about the validity of the state that you own and you have access to. So, coming back to the question. For the state you have access to and the state you need to run the validation, you're always able to analyze, do you have the access to the latest global state or not? And if you don't have access to the latest global state, the contract validation will fail, notifying you that you need more global state data and you need to go somewhere and download it. But if you, for the parts of the state which are not related to the state you own, which can be deduced through the contract schema, there might be a global state which exists for the contract and which you don't have access to, but you don't need this global state because it's unrelated to the validation procedures of the state that is you owning and that you are actually validating. So this divergence in the contract state is solvable. Like it's kind of, it's one of the tasks I'm planning to do when we will finish this. Most of the development work is to scientifically prove that actually there is a convergence of all these partial views on the smart contracts and their global state, and that there is no internal contradictions, even though that each participant have a very partial view, not very good, but a partial view of the contract state. Sorry, the answer was really elaborated, but let me try to rephrase it once more. For the state which you need to access to do the contract validation, which is a part of the schema and the scripts, you always can deduce, do you have the latest state or not? For the state which is not part of the validation procedure, you don't have information, you may not have information, is this global state the latest one or not, but you are not using it in the validation anyway. Was the last attempt an answer, or still it's not quite clear?
Let's see. So I guess the idea is that the global state is owned by the contract issuer.
Well, it's not owned by anybody, and it also can be created not just by a contract issuer.
Well, that's a bit contradictory to a lot of things that we have been saying about RGB in the first place, like there should always be an owner. So that's kind of incorrect from now on.
If something can be owned, there should be always a well-defined owner. If something is not owned, there might be no owner. For instance, the name of the asset is not owned by the contract issuer, but the contract issuer has an ownership over the right to change the asset name.
Not sure I understand the philosophical difference, but it sounds very like Eastern yogi wisdom, so I will accept it.
Well, I mean that when you create a global state, the state from that point is global. I'm not calling it unowned, but it's globally accessible. It can be hidden through the zero-knowledge commitments. It's still designed to be globally accessible and seeable. But when you try to change the global state, you need to have the right to do that change. So the right of changing global state is owned. But the global state, I can't say that it's owned or unowned. It's just a thing that exists.
Okay, so you're basically equating ownership with rewriting rights, which is also so changing rights, which is but not by public disclosure of the change. So if you can change something in public, it's not directly ownership.
Yes.
Okay.
Well, probably any change requires ownership, at least over the right of that change. So you can't change anything in the smart contract without ownership.
So in that case, if I can change the name, I own the name then.
You own the right to change the name.
It's like the difference between knowledge and right, or ownership and knowledge. Because
well, let me explain why this difference is important. Because like it's all about the terms. So there is a state which can be changed by just an owner of that state. So the state is literally attached to the ownership. We call it own state. And there is this new thing which we call a global state. And it's not directly attached to the ownership, but it's a form attached indirectly. So it exists, but to change it, you need another own state. For instance, an own state of a right start to change the global state. So it's more indirect ownership. And that's in direction I'm saying that you need to have the right to change the global state. That's the indirection of this thing. Why it was important to differentiate and why it wasn't working without this differentiation. For instance, you issue an asset, and in Genesis you define the issuer assigns himself a right to change the name of the asset. And he attached to that right the actual asset name, the current asset name. But if somebody issues an asset without ability to change the name of the asset, where the name of the asset would exist, you have nowhere to attach to do the assignment of the name to the right of the name change, because the right of the name change doesn't exist. So you can't give an initial name of the asset. And that's why it was important to differentiate the global state from the own state, because the global state is the state of the current time of the past, while the own state is the state of today, which can be changed into the future. Sorry, I'm probably explaining that in a very weird way, but
It's fine. We will get there, and eventually, hopefully. Pantamis had a comment. So if you need new information about a mutation of the global state, mutation you mean like change in the global state, I guess. You just look at the UTXO of the person that has the right to change some part of it.
Correct.
Okay.
And if it wasn't executed, you knew that the global state wasn't changed because the right of changing the global state wasn't executed.
Nice. Cool. So, any more questions? Nick, come on.
Yes, so my question, if I understood right, it's a owned state. It's that the code and saved only by one person on some subject. So if it's not shared to everybody, why is it limited to such a small number as 64 kilobits?
Because the history of it is maintained forever. So for instance, I'm sending you an asset. So my own state is cancelled, and now you have your own state emerging from my own state. And then you send the asset to Giacomo, and the same happens once again. And Giacomo will see the history of all our past states. He wouldn't be able to read how many assets we had, because they will be hidden behind the zero knowledge, but still he will run the validation procedure on that state. And the state will be kept forever. So if the state, each state piece will grow in the size, more than 64 kilobytes, we will have an explosion of the history size of the historical data. So it's pretty much the same protection as block size. Okay, I get the idea. So, but I just deep dive in RGB, but for this case, for example, if I have an asset on the RGB and I have received some coin from one person, from another person, I have two different states, right? Histories. And I hold both of them, right? Can you repeat once again? Sorry. I mean, for example, we have an asset over RGB, right? Yes. We have some Alice and Bob. They both sent me some coin on this asset, yeah. And so I should hold both of their histories, right? Yes, you will have a graph of the history, not just a linear history. Okay, and then when I send to second person, to third person, I will combine these graphs of the Alice and Bob together. And okay. So they will aggregate over the time. Okay. Okay, so according to this, is it possible to resolve these limitations maybe by zero knowledge proof? Theoretically it's possible, but it's a matter which will take another couple of years. So for now, we are just doing we are doing RGB without that, and maybe some future protocol will be leveraging zero knowledge compression of clients. Okay, thank you. And the last question, it's is it this release like 10.10 0.10 is it ready for like production use for the users or for the developers trying the like real system, real Bitcoin or not? Well, the simple answer, I don't know, meaning that like I assume it can be used, but if you use and lose the assets, don't blame me. I will personally try to do mainnet assets, and I know people who will be doing mainnet assets using this release. But it's a software which will never be used in production, and even 10 years after Bitcoin was created, people were saying that it's still a beta software. So it's really hard to find the boundary where it's not beta anymore or still experimental. So RGB is experimental. I would say it like this. 0.10 is the final consensus release. This is experimental software, but it can be used for some real-world assets with the precaution that everything can go wrong. I mean, I think the condition of this to code release, it's when you are going to support and all the contracts made by this release will be valid in future by future release, right? Yes, that's the goal of this 0.10. Okay. It can be broken by the fact that there will be some critical bug discovered, but hopefully it wouldn't happen.
Okay, thank you.
Great. Anything else? I think we can then wrap this up. Thank you, Maxim, for
Thank
2
you
hours.
for coming and listening.
Thank you, Maxim.
It's been really great. Thank you guys for joining us. I'll upload the recordings to our channels as soon as they're ready. I need to fine-tune a couple of things. And see you next week. I'll announce the next dev call next week. Thank you.
Thank you.
Bye-bye.
Bye-bye.